Hi everybody, and welcome to our module on hypotheses testing. We're going to be introducing hypothesis decision making and t-test. As we've noted in previous modules, the whole purpose of inferential statistics is to help us make inferences about a population because it's impractical and impossible in many cases for us to collect data from every single person within a population. So therefore, we use hypothesis testing to make those inferences. So we use sample data to evaluate the validity of a hypothesis about a population. So what we do is we state the hypothesis about our population, what do we believe is going to happen, and then we predict expected characteristics of the sample based on that hypothesis. Then we obtain a random sample from the population and we compare the obtained sample data with the prediction made about the hypothesis. If it's consistent, the hypothesis is reasonable. If it's discrepant, then the hypothesis is rejected. So in a basic experimental design, you typically know some information about your population. The basis for experimental situation for hypothesis testing is that it's assumed that the parameter, the population mean that is known for the population before treatment. The purpose of the experiment is to determine whether or not the treatment has an effect on the population mean. So as you can see, we have a standard deviation of 3 and a population mean of 16. We have treatment, and then we have a standard deviation of 3, but we don't know what the mean is in this particular population because we can't give treatment to every single person and then determine what that is. Similarly, you can see from this point of view of a hypothesis test that the entire population receives the treatment, not likely, and then a sample selected from the treated population. In an actual research study, the sample is selected from the original population and a treatment is administered to that sample. The idea being that we can't, as I've said before, pull the whole population for treatment, so we pull a sample from that population and then make inferences about the population from the sample. If we have a random sample and we have enough people within that random sample from the population, remember our central limit theorem of at least 30 in most cases, then we should be able to make some inferences to our population. So we have 4 steps to our hypothesis testing. Step 1 is state the hypotheses. That's plural, so if you just have one, it'd be hypothesis. Set the criteria for a decision, collect the data and compute a sample statistic, and then make a decision. So, as the name implies, the process of hypothesis testing begins with stating a hypothesis about an unknown population. So what we're going to have is a null hypothesis, which is designated with a capital H and a subscript 0, and it states that treatment has no effect. There's no changes, no difference, there's no relationship between the independent variable and the dependent variable. Whereas an alternative hypothesis, H1, states that there is a change, a difference, a relationship in the general population. So step 2 is to set our decision criterion. And in this particular case, we're going to use the data from the sample to evaluate the credibility of our null hypothesis. The data either supports the null hypothesis or tends to refute the null hypothesis. If there's a big discrepancy between the data and the null hypothesis, we can conclude that the null hypothesis is wrong. So in order to formalize our process, we use the null hypothesis to predict the kind of sample mean that should be obtained. Specifically, we determine exactly what the sample means are consistent with the null hypothesis and which sample means are at odd with our null hypothesis. For example, the null hypothesis states that a supplement has no effect and the population mean is still the mean of 80. If this is true, then the sample mean should have a value of around 80. Therefore, a sample mean near 80 is consistent with the null hypothesis. On the other hand, a sample mean that's very different from 80 is not consistent with our null hypothesis. To determine exactly which values are near or very different from 80, we have to determine all the possible sample means that could have been obtained if the null hypothesis was true. So for example, let's say that we have a distribution of sample means that's n of 25. According to null hypothesis, this distribution should center at the mean of 80. The distribution of samples is then divided into two sections. Sample means that are likely to be obtained if it's true, and sample means that are close to the null, and sample means that are very unlikely to be obtained if the null is true, and the sample mean that are very different from the hypothesis. So this figure shows the distribution of the sample means divided into two sections. Notice that the high probability samples are located at the center of the distribution and have sample means close to the value specified in the null hypothesis. On the other hand, the low probability samples are located at the extreme tails of the distribution. After the distribution is divided in this way, we can compare our sample data with the values of the distribution. Specifically, we can determine whether our sample mean is consistent with the null hypothesis. That is, are the values in the center of distribution, or whether our sample means are very different and at the tails of our distribution. Now, to find the boundaries that separate the high probability from the low probability, we have to define exactly what's meant by low and high. To accomplish this, we select a probability value. It's also known as the level of significance, or alpha level, for the hypothesis test. The alpha value is the small probability that is used to identify the low probability samples. So by typical standards, we tend to use an alpha level in social sciences of 0.05. There's also a sample alpha set at 0.01 or 0.001. So for example, with an alpha of 0.05, we can separate the most unlikely 5% of the sample means, the extreme values, from the most likely 95% of the sample mean, or extreme values. So the extremely unlikely values, as defined by the alpha level, make up what's called the critical region. These are the colored sections on the chart. The extreme values in the tails of the distribution just define outcomes that we're not expecting, the ones that aren't consistent with our null hypothesis. They're very unlikely to occur if the null hypothesis is true. So, because remember, when we talked about mean and median and mode, we talked about that most of our scores in a normal distribution will fall within that center part. So the outsides are our extremes, or unlikely ones. Whenever the data from a research study produces a sample mean that's located in these critical regions, we can conclude that the data is not consistent with the null hypothesis, and we would then reject our null hypothesis. So technically, the critical region is defined as sample outcomes that are really unlikely to happen and would demonstrate that there's no effect. Reversing this, we can say that we can also define the critical region as sample values that provide convincing evidence that the treatment did not have an effect. For example, the regular population of elderly adults has a mean score of the mean of 80, right? We select a sample from the population and administer a treatment, say this blueberry supplement, to individuals in the sample. What kind of sample mean would you convince you that the treatment had an effect? Well, it would be obvious that the most convincing would be a sample mean that is really different from the mean of 80. In a hypothesis test, the critical region is determined by the sample values that are really different from the original population. So it's really important to remember that in research, we are really focused on this idea of falsification, that we're really trying to reject our null hypothesis, because our null hypothesis is always saying that there's no difference. And so when you can really wrap your head around this kind of idea of double negatives, it'll be much easier. But a null hypothesis is saying there's no difference, there's no effect. And so really, we're kind of trying to reject our null, but we don't actually say that in research because that would be fishing and that wouldn't be appropriate. But what we want to do is make sure that when we're setting our hypothesis up, that we're really determining that it's not just by chance that we got the results that we got. We want to set up our hypothesis in such a way that we're really saying, okay, if there is no effect, this really wide range of scores are possible, and it's only those extreme scores that make it likely that the treatment that I used had the impact that I was investigating. So let's take a look. So to determine the exact location, like I said, of this critical region, we're going to use an alpha level or p-value or significance level. And we're going to also look at the distribution of means and look at the table B2 in the back of your book to determine what the precise boundaries are. Well, B1 if you're doing z-scores, and B2 if you're doing t-scores, which we'll talk about later. Let's look at it from a z-score, because you're familiar with the z-score concept already, which is our standardization score, right? So with an alpha of 0.05, for example, the boundaries that separate the extreme 5% from the middle 95%. Because the extreme 5% is split between the two tails on the distribution, there's exactly 2.5% or 0.0250 in each tail. In the table, you can look up the proportion and find your z-score like we've done in the past, and you'll see that there's a z-score of 1.96. So for any new normal distribution, the extreme 5% of the tails exceed z plus or minus 1.96. The values define the boundaries of the critical region for hypothesis testing using the 0.05 level, as you can see in this chart. Okay, so to continue, step 3 is to collect the data. So you're going to always collect your data after you've stated your hypothesis. So it's inappropriate, unethical, incorrect, wrong to collect your data and then make a hypothesis. You want to have your hypothesis before you make you collect your data. The other thing is that most of us go into research having a theory about what we think is going to happen. And in this case, you have to remember the null hypothesis, because the null hypothesis, as I've already said, says there's no change, no difference, no effect. So if I'm researching the impact of, say, clinical supervision on if it helps people have better skills, that's not what I'm going to say in my research. What I'm going to say is that for my null hypothesis, that there's no impact clinical supervision on a counselor's efficacy. Because really I'm trying to find out there is, and because I can't ever prove anything in research, because I can never be sure that I've accounted for every single variable, all I can do is disprove if a certain variable that I'm interested in had an effect or not. So I'm always using that rule of falsification. So data is always collected after the hypothesis is stated. Data is always collected after establishing my decision criterion, my alpha level. And this sequence is going to really ensure that you have objectivity and that you're practicing ethically. After we've done that, then we'll compute a statistic. For example, a z-score or a t-value, t-test. We'll be talking about those, but there's many more after that. ANOVAs and all sorts of other wonderful tools we're going to be talking about in the near future to show the exact position of where my sample falls. So, let's go to step 4. So step 4 is we make a decision. If the statistic is located in the critical region, the null hypothesis is rejected. If the statistic is not located in the critical region, then the researcher fails to reject the null hypothesis. Okay, we don't accept the alternative, and that's really important to remember. We either reject our null hypothesis, or we fail to reject our null hypothesis. So it's important to know that language. Now, there's going to be uncertainty and errors in our hypothesis testing. It is an inferential process, so that means it's using a very limited amount of information from a sample to make a conclusion. And our sample allows for us to draw conclusions, but errors are possible. You know, it could be that one kind of fluky sample that really isn't representative of your population. There's 2 types of errors. There's the type 1 error, and this is where a researcher rejects a null hypothesis that's actually true. Okay, so that means that your score should have fallen within that middle section, but for some reason you got that outlier and you rejected the null hypothesis when it was actually true. You can also conclude that a treatment had as an effect when it didn't have an effect. And the alpha level is the probability that a test will lead to a type 1 error. If you remember back in that chart, you had the 0.05, right? Your alpha, 0.05. And so that's saying that I have a 5% chance that I found a score or a sample that did not accurately represent the population. So I have a 5% chance of being inaccurate. I have a 95% chance of being right, and I have a 5% chance of not being accurate. If I choose an alpha level of 0.01, I have a 1% chance of not being accurate, and I have a 99% chance of being accurate. So type 2 errors. The researcher fails to reject a null hypothesis that was actually false. Researchers failed to detect a real treatment effect when there was actually one. And type 2 error is a probability is not easily identified. So, hypothesis testing, oh, we already did that one. Let's go back the right way. Okay, so here's a chart that's in your text that I think is really helpful. So in this one you can see that the null hypothesis in the first row is really true. So there was no effect, right? So in this one, if I accept, even though it's called fail to reject, my null hypothesis, you would fail to accept the null when it's true and there's really no difference between groups. So that's good. What you want to avoid is this second one over here where you're rejecting the null hypothesis when there actually was no difference. So that one's a problem. You don't want to do that. And so there's some ways that we can control for that. And then the null hypothesis is really false. Uh-oh, we made a type 2 error. And this is where it's called your beta. And we'll talk about the betas a little bit more later. But we accept or fail to reject a false null hypothesis. The other side of that is actually good. You reject the null hypothesis when there really are differences between the two groups. And this is called our power, which we're actually going to talk about some more tonight in this module. All right, so here for the z-scores, these are the locations of critical region boundaries. So remember, we've talked about z-scores for a little bit now. So +1 and -1.96 is within that one z-score, and then you have 2.58, and then you have 3.30. You've seen this chart in a different format where I said it was 95% of the scores here, it was 99% of the scores here, and it was over 99, or yeah, it was 95, 97, 95, 99. So you remember those charts where you were looking at how the scores fell within those charts. Now, remember when we were talking about z-scores, we really use z-scores to quantify inferences about the population, right? What's the obtained difference between the data and the hypothesis, and what's the deviation between the sample and the population. Now, this is a new letter. M can also be used for sample mean, so I don't want to confuse anybody, but you can see that as an X bar, or you can see it as a capital M. And then this is the mu, and this is the population mean. So this is the standard deviation of the mean. So we're going to use the normal table, which is your first table in your book, B1, and to find the critical region of the z-scores when n is greater than 30, or when the original distribution is approximately normally distributed. And we know that when we get really, really big samples, we can expect that they are. But there's some problems with z-scores. Z-scores require more information than researchers usually have. We have to know our population mean, we have to know our population standard deviation, and researchers usually only have the sample data available. So that's why we're going to use something called a t-statistic, or t-stat, t-test. A t-statistic is the alternative to a z, and t-test might be considered to be an approximate of the z. And what it does is it uses the estimated standard error in place of the real error when the value of the population mean is unknown. Now, the t-stat, as I mentioned, uses the sample mean estimates with the population mean, and the standard error is described how much difference is there reasonably to expect between the sample mean and the population mean. So again, just a review of the estimated standard error. We're going to use S2 to estimate the population, so we're going to use the standard error to estimate the population error. And this is the formula, just a review from what we've already done. And the estimated standard error is used to estimate the real error within the population. And then with the t-test, we then use the estimated standard of error in place of the population mean. And the t-test is used to test the hypothesis about the unknown population mean when the value of that standard deviation is unknown. Now we do need to remember this idea of degrees of freedom. So degrees of freedom is the computation of the sample variance, and it requires that we know the sample mean first. So when we use the n-1, remember we're including all of our scores and giving ourselves a little bit of room to play. So DF, you'll see that in your interpretation of scores, is known as degrees of freedom, and it equals n-1. So it's your sample size minus 1, and it gives you a little bit of room for error. So when we do a normal distribution, that's this really spaced line here, okay? That is a normal distribution. So our mean, right? Our mean, median, and mode would all be in the same place on that one. For a t-distribution, when we have the degrees of freedom at 20, which means our sample was actually 21, we can see it deviates a little bit from the normal distribution. It becomes a little bit flatter and a little bit more spread out, right? And then when we have a t-distribution, degrees of freedom of 5, which means our sample 6, is even flatter. So as the sample size goes down, it does impact our t-score's ability to mimic the normal distribution. And that's important to remember because that will impact how we interpret this. So for family of distributions, 1 for each value of degree of freedom. So when you look at your table B2 in the back of your book, you'll see that there's these t-values for hypothesis testing. And these approximate the shape of the normal distribution. The flatter the normal distribution, the higher the lower the t, the degree of freedom, and the higher the degree of freedom, the more it replicates a normal distribution. So just remember that the smaller the DF, the flatter it is and the less likely it is to really mimic that distribution. And the higher the DF, the more likely it is to mimic the distribution. But we can still make some inferences from it. So here's an example of a t-distribution for degrees of freedom of 3. So our sample size would have actually been 4. This is for a critical value or alpha level of 10, because you can see 5% and 5%. So when I look up the t-score for a degree of freedom in the back of the book, I should find that the t-score is 2.353. Now, how do we use a t-test when hypothesis testing? Well, first we got to calculate our t-test, which we've talked about, and then we have to determine what we know about this. So when we're looking at the basic research situation for a t-test, we know, as I mentioned earlier, we have the known population, right? And we have our unknown population after treatment. So again, we're going to go over these 4 steps, and I'm going to walk you through using a t-test. So you state your null and your alternative hypothesis, you select your alpha level, you locate the critical region, and I personally find it really helpful to draw this out because I need to see these things. And then you calculate your t-test, and then you make a decision regarding your null hypothesis. So here is the critical region for a t-test distribution at the alpha level of 0.05 with degrees of freedom of 8. Okay? So here, what it's saying is that when I look up the t-test, it's telling me that if I get any score, if I get a t-test that's greater than 2.306 over here, or less than negative 2.306 over here, I'm going to have to reject my null. If I find a score that, or if I get a t-test, or t-score, t-statistic that's between 0.0306 and positive 2.306, if it falls between those two scores, then I have to fail to reject my null hypothesis. So this score and lower, this score and higher, I'll reject. Anything in between, I fail to reject. So let's look at an example. Let's pretend that a group of infants, 9 of them to be exact, are given an attractive faces test. This is actually a famous research study. So you have 9 infants, they're given 20 seconds to look at a series of different faces that adults had previously screened as attractive or not attractive. And so the theory was that if the null hypothesis was there would be no difference in how much time the infants spent between the different types of faces, attractive or unattractive. And so they estimated that it would be, 20%, be split in half. So if, there's no difference in 10 seconds, that they would look at all the faces about 10 seconds. So here we have this written out. So N of 9, sample of 9, our sample deviation, our sample mean is 13 seconds, and our sum of squares, which we talked about why we have to do squares of deviation, is 72. We don't know our population mean or our standard deviation for our mean. So we're going to state the hypothesis and select an alpha level. So null hypothesis again is that there's going to be no difference in the amount of time that the infants look at it. We're estimating that no matter what type of face it is, they're going to look at the face about 10 seconds. Whereas the alternative hypothesis says that it's not going to be 10 seconds. It's going to be greater than or less than. And we set our critical value, our significance level, or alpha level at 0.05 for 2 tails. So then we're going to locate the critical region. We need to use the t-test because the population's information isn't known. So remember our degrees of freedom. So n minus 1, 9 minus 1 equals 8. So table B2, I look up 8 degrees of freedom. The t-value is greater than 2.306 or less than 2.306, right? And so that's going to be my rejection zone. Okay? So calculate my t-statistic. Calculate the sample variance, sum of squared deviations. So we have standard deviation, sum of squares, n minus 1, sum of squares difference, so 72 divided by 8 equals 9. Calculate the sample variance, so that's my sample mean with the standard, the square root of my standard deviation up here divided by 9. So again, that's 9 right over here divided by 9n equals 1. The square root of 1 is 1. Compute the t-test for the sample data. So now we're going to use x bar minus the population mean divided by the standard deviation. So 13 is our mean for the sample that we collected. 10 is the population or the hypothesis that our population is, and we're going to get a 3. So this is our t-stat, it's a 3. Now, if we look back at this thing, if we have a 3, a positive 3, what are we going to do with that? We're going to reject the null hypothesis. So therefore we have to reject the null hypothesis because our 3 falls right here. And that means we have to reject it. Okay, so that just walks you through the 3 steps. Now let's look at it from a directional hypothesis or one-tailed test. Non-directional is what we just did, t-test, right? However, sometimes directional are used, and so here's the 4 steps carried out again. Okay, so same idea, infants looking at attractive faces, n of 9, our sample mean is 13, our sum of squares is 72. We don't know the population mean or the population standard deviation. Our null hypothesis is going to be that we are going to say that, kids are going to look at all faces less than or equal to 10 seconds. Whereas the alternative is going to say if it's attractive, they're going to look at them for more than 10 seconds. And we're feeling pretty confident about this one, so we're going to use a 0.01 one tail. So that means that when I go to my chart, right, I'm going to see that that equates, when I say, this 0.01 alpha, that equates with a 2.897 in that chart in B2. And so anything that's above 2.897 is going to get rejected. And then I do my calculations. Remember, when I do my t-test, because it's not going to be any different than what I had here, I'll calculate my t-test, and I'm going to come up with a 3. And when I come up with a 3, I'm going to know to reject my null hypothesis, because I'm going to say there is a difference in how long these kids are looking at these attractive or unattractive people. So there's some basic assumptions about t-test. Values in the sample are independent observations. The population sample must be normal. So the larger the sample, the larger the sample, we have way more kind of leeway for mistakes. So, it's like, just think about your larger sample as being more forgiving. And remember that sample size and sample variance have an impact. So the larger the sample, the smaller our error, because we've had more opportunities. It's kind of like if you have, 20 test grades versus having 2 test grades, you know, I would rather probably be in the class with 20, because if I bomb one of them, it's not going to have nearly the impact as if I bomb one of my tests in a 2-test class. So that's kind of a way to think about, you know, sampling error, that the larger the sample, the smaller the error. The larger the variance, the larger the area, so the more deviation. Remember when we looked at the elementary and the middle school scores, you saw that process. All right, so let's do a learning check. So when your sample size is small, less than 30, the t-distribution is what? So remember those pictures I showed you about what happens with the t as it gets smaller and smaller when our degrees of freedom drop. So if we can remember, that means that it's flatter, more spread out than the normal z distribution. So the larger number of sample we have, the larger n we have in our sample, the better. And once you hit about 120, when you hit 120, it's about the same. So once you get a sample size of 120 or more and you're using t-test, you're good.